Hello, my name is Matthew Farah, and this is my Lab 4 bar magnets report. So to begin, the purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet. We also had to compare measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields. In this lab, we used a bar magnet, a smartphone with a magnetometer app, a meter stick, and tape. Here's a preview of the results. So the magnitude of a net magnetic field increases as distance decreases. The observed off-axis magnetic field is 0.065 teslas, and the simulated off-axis magnetic field is 0.0528 teslas. Here are the fundamental principles that have been used throughout this unit and in this lab. We have the Butte-Savart law, which states the magnetic field B at a point in space is directly proportional to the current flowing through a conductor and inversely proportional to the distance between the source of the field and the observation point. The magnitude of the magnetic field of the loop has the shape of the on-axis magnetic field of a dipole. And in this lab, we have the system being the observation point or the magnetometer on the phone. And the surroundings were the bar magnet, which was producing the field. So here's the procedure for this lab. First, we had to compensate for magnetic north by orienting the phone so that the magnetometer app had the x component of 0. Then we had to find the magnetometer chip in the phone and then measure the on-axis magnetic field by measuring the distance between the magnet and the magnetometer, where the magnetometer is on axis to the dipole axis of the magnet for the following x components. We had 20 teslas, 70 teslas, 120, 170, and 220. We also had to measure the off-axis magnetic field by measuring the on-axis distance between the magnet and magnetometer, such that the magnitude of the net magnetic field is 100 teslas. To finish measuring the off-axis magnetic field, we had to measure the on-axis distance between the magnet and the magnetometer, such that the magnitude of the net magnetic field is 100 teslas. We did this by recording the y component of Earth's magnetic field, applying this distance in the y direction, and moving the magnetometer to the new distance, calculating the magnetic field at this new point, and repeating this process twice. Here's the Excel sheet we used in this lab to document and store our data. You can see on the graph on the right, the observed and expected results are pretty similar. There's a little deviation on the expected results that curve near the bottom right of the line. But for the most part, it is pretty similar to what we were expecting. And some of the flaws can be explained later by the possible error section. On GlowScript, we recreated this experiment by creating a model in which we had to create a function for the magnetic field and visualizing the magnetic field with different errors and vectors. And here on the right side, you see that we had to edit one of the lines to match one of our observed measurements in order to create an accurate model. And on the right side here, we have the program that GlowScript creates for us. We can see the different perpendicular magnetic fields as well as the 45-degree at distance d. The result was a magnetic dipole moment of 2.73 amps squared. The experimental magnitude on the off-axis was this vector shown, and we also had the simulated magnitude, which was created by the GlowScript code. As I mentioned earlier, there were some possible sources of error that caused the change in both observed, expected, and the simulated data. Some of these being other magnetic forces interfering with the system of the magnet and the phone, an inconsistent phone placement and movement, and application errors stemming from the magnetometer app not being perfect. Now here we'll conclude with the discussion questions. The first one asking, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So the magnetic field in the x and y directions would have changed because magnetic north wouldn't have been accounted for, but since the phone is flat on the table surface, the z-coordinates still would not change. Second question states, what if you were to stick two identical magnets together end to end, and run the experiment again? How would you expect your measurements to differ? So by combining the two magnets, the magnitude of the field would increase to almost double since we're having two magnets in one, basically. The distances for each magnetic field would decrease due to an increased magnetic field magnitude from the two magnets.